All right. Hi, everyone. My name is Zach Penrod. It's within Sales and Marketing Department here at InMotion US. Welcome to this session looking at the why and the how of replacing traditional hydraulics with electric actuators. It's my pleasure to introduce Kirk Martin, Sales Director for the mobile machinery sector at Evolix, a company specializing in electric actuators for on and off highway applications with a key focus on full electrification. Kirk is located in South Carolina and has been in the industry for over 20 years. Throughout the session, please utilize the Q&A tab on the top right of your screen so that we can easily track the questions to get them answered. And with that, I will turn it over to Kirk.
Thank you, Zach, and thank you to Zappy and InMotion for inviting me to join this conference. I look forward to sharing a few minutes with you, talk about electric actuators, particularly on the why and the how. Just a quick agenda, a little bit introduction, brief introduction. I'll kind of get into the why, and then also a little about actuators 101, just kind of electric actuator basics, how they're made up, what components go into them, different options, that type of thing. And then finish up with kind of how to fully electrify a machine and no hydraulics whatsoever. So just a brief introduction. Obviously, the electrification trend in mobile machinery is large, and we're all familiar with. Obviously, we're a Future Electrification Conference. We're addressing that subject a lot of different ways. For us, when we go talk electric actuators, typically OEMs or machine builders do their drivetrain first to get fully zero emissions, and then they kind of look at electric actuation to replace the hydraulics to go more efficiency or no oil or different ideas. I'll talk about the whys. So I'll dive in next into kind of 5 main reasons why customers look at going electric actuators versus hydraulics, and then also the 7 steps by a machine if you are challenged with trying to replace those hydraulics. So number 1, kind of why electric. I'm going to talk about 5 reasons, maybe a 6th one. Obviously, energy efficiency is probably the most common one, and eliminating oil. Those are probably the 2 most reasons why people want to do it. Obviously, going into municipal areas, they don't want oil, different situations. I'm a golfer. I don't like seeing oil on my golf course. I'm also own a small tractor. I don't like changing the hydraulic hoses. So lots of reasons, but those are 2 of the big ones. I'm going to talk a little bit more about efficiency. Controllability is another one people don't necessarily think of, but as you go, obviously the electric actuators are a lot more controllable typically than the hydraulic package, especially if we go into more and more autonomous stuff. I'm going to talk more about controls a little bit later in the presentation. A couple other ones that sometimes people don't think about. The bombs, obviously a lot simpler, lower typically on an electric machine. There's no filters, no hoses, valves, that type thing. Just a lower, simplified package. Also, no maintenance. Typically, there's not a lot of maintenance on an electric actuator. Maybe some grease in the gearbox. It doesn't need to be replaced. The grease on the screw typically doesn't need to be replaced. So, in general, it's a pretty much maintenance-free system. The only other kind of reason some people look at it is if it's hydraulic package on the end of maybe the back of a combine, for example, and you just don't want to run hoses all the way back there. It's easier to run wiring, and you can just have an efficient package back there, and you just don't want to run hoses. So maybe just accessibility is the other reason. But those are kind of the 5 main reasons. What your reasons are is always different. Each customer is different, but these are kind of some of the ones we get into. When we talk about efficiency, I got pneumatics on the left, obviously. Don't run into that too often, but hydraulics, I'm sure there's people have different ideas of what the efficiency. We're kind of looking at typically 44% efficient in that range, depending on the system complexity. So with electric actuators, we'd come in. I guess I like to caution here, a lot of people think electric actuators are 90% efficient maybe, or higher efficiency, but you've got 3 points that you lose energy. You've got your motor, you've got a gearbox, and then your screw. So you do lose efficiency in all those places. So typically our actuator is going to be 60 or 70% efficient, depending on the setup. So that's kind of what we use as a guideline. And then also the one thing that electric does give you fairly easily, depending on the application, is you can get regen through the actuator, so you can get the net impact efficiency is a lot higher. But it has to be the right application. Obviously, a scissor lift we have pictured here is perfect. You got loads going up, you got load coming down. Maybe a forklift on a mast, you're good loaded coming down. So things like that, you can get some regen if you get the right setup on your motor and actuator. So you can get your net efficiency. But in general, 60 to 70% efficiency on the actuator. Moving on here, just a little bit of slide on the system complexity. You guys know this, but for us, basically, in general, you basically have a controller and an actuator. Sometimes the controller is integrated into the actuator. For a lot of actuators on the marketplace under 1 ton force have integrated controllers already in them. So it gets really simple then. Just have to run wires out there. All right, just getting into actuators 101, I call it. Like I said, I'm not going to go into a lot of detail, but just kind of give people an idea of what makes up an actuator. So number one, you typically have, like I said, there's usually some type of controller telling the actuator where to go, when to go, how far or how fast. And then you got a motor. And then typically you have some type of drivetrain, so either belt or gearbox. I'll talk a little bit more about those later. And then that drives the screw, whatever it is. And then the screw has a nut attached to it. And then the nut is attached to the push tube. And then as the screw rotates, the nut translates and then pushes your push tube out. Typically in a lot of our actuators and a lot of actuators out there, there's an anti-rotation device between the nut and the guide tube so that you don't transfer torque to your front attachment or to your frame. Some actuators don't have that, but in general, all of ours do, and a lot of actuators do have that. If you don't have that anti-rotation, this push tube will rotate. So I'll dive in. The first is an Acme screw. It's kind of the most basic type of screw available. It's low cost, smooth movement, low efficiency. You don't have any rolling elements between the screw and the nut. So it's all friction, low leads. The advantages of these are, like I said, the low cost, but they're also, some leads will not back drive, so you don't need a brake. So in some vertical applications, they work pretty nice. You don't need a brake in your system to hold the load. Once again, various leads available. These are very common in the smaller actuators under 1 ton or even under 3,000 newtons or so. Typically use some type of ball or Acme screw. And moving on into ball screws. So ball screw, you have a nut and a screw, and in between those you have balls. And so your friction is very low, your efficiency is high. It's a very cost-effective design. These will back drive, so you'll need some type of brake to hold your load when it's lit and when it's raised. It's point-to-point contact, so that impacts some of your impact resistance and that type thing versus other methods. And then there's various leads available. Typically in the mobile machinery market, we're using 10 to 20 millimeter leads, most commonly around 10 millimeter leads. It just kind of matches up with the speeds everybody wants to go. Obviously, leads, if everybody doesn't know, is how far the screw will translate per revolution. Moving on to roller screws. There's a few people out there manufacturing roller screws. Evolix is one of them. It's just another option. Typically, we try to start with a ball screw because it's most cost-effective design. But in some cases where they really need power density or shock load resistance, the roller screw is an option. It's quite a bit more costly. It's also less efficient. So we try to start with ball screw ourselves, but there is a lot higher initial cost. These are very expensive items, but it is a feasible option if it's really high impact or high power density. Typically, they're around 5 millimeter leads. They also will back drive. They're efficient enough that they'll back drive, but they'll typically need a brake on those also to hold the force. Let's move on real quick on some of the transmission types. We have a belt drive. Typically, it's like a poly chain type of belt in there, so no backlash, pretty good life. You don't have to retension it. A belt drive gives you a little bit shorter cross section through the transmission drive housing. And it's also typically used at higher speeds. So if you want to go faster, typically we go with it's only got a 2-to-1 ratio typically, or maybe 1.5 to 1, depending on the setup. But it will back drive again, so a brake would be required. Now the spur gears, both the belt drive and the spur gear gives you kind of what we call a U setup. So you got your linear unit, you got your gearbox, and then you got your motor. So you get a U setup. Obviously the space claim, I'll talk a little bit more later. But these can do high speed capabilities. There's various ratios available from different manufacturers where we do 4, 10, and 25. In mobile, a lot of ours are around 10-1. Seems to kind of settle in where we need to be. Once again, these will back drive, so there will need to be a brake somewhere in the system for holding. And once again, it gives you the parallel shaft U shape. Another one that's not quite as common, but certain applications it works out pretty nice. If you're inside of a tube or inside of a boom extension tube or something like that. Here you have the linear unit. You can either have a direct drive the motor right to the linear unit or have a planetary gearbox in between. So that's just some different areas you can go. One I didn't talk about, right angle is available also, either a bevel box or a worm gearbox, kind of standard units out there. You can put it in between the actuator and the linear unit once again to get a 90-degree setup, depending on your machine fitting it in there. Motor controller considerations. They're kind of, it's a broadening market. Obviously, we're working a lot with InMotion, a lot of our projects. Your voltages will be all over the place for different applications. I'm going to talk a little more about voltage later, but typically, in general, you typically have a brushed DC motor for the low duty cycle applications, and then we jump up to more high performance motors for the higher duty cycle or higher performance applications. And obviously, there's more and more development as we get into more DC or DC powered machines or battery powered machines. Typically, there's some type of integrated controller or an external controller. Once again, we're using some InMotion controllers that are external. On some of our smaller actuators and some of the other actuators in the market, they do come with integrated controllers, so they can communicate with CAN bus and that type thing. So it's just the option you got to do. Sometimes it may just be a toggle switch and you don't need a controller necessarily. So it's just a manual stop. So it just depends on where you go. Some unique functions that maybe are starting to become more and more requested. Float mode is kind of one. If you got some ground engagement and you're trying to keep a certain distance to the ground, you may need to control that actuator quite a bit. You're just doing it with the motor typically. Another one where we have to get work on is the parallel function. So if you have two actuators in parallel, you've got to synchronize them. So typically the controller has to be able to do that send a message between the two controllers. Once again, some of the integrated controllers have that function built in. You also may have start, stop, soft start. So maybe on a hood for a big machine or something like that, it's going down. You want to have it move fast, but when we get down to the end, you want to have it to close nice and soft. We also get into E-clutches, where you just kind of want to overload if you get an obstacle in the way. And this is just measuring the amperage. You can kind of set this typically, and it'll kick it off, just some functions. And then typically, if we are doing any type of positioning programmability where we're trying to put in a position, we'll need some type of absolute position control. Once again, the integrated controllers on the smaller actuators typically have that built in. And then on the larger actuators where we have an external controller, typically we have to put some type of absolute position control on the motor or the gearbox or somewhere in the drive package, so that we can know where the actuator is position-wise. So that's just quick actuators 101. Now I'll kind of get into kind of steps to fully electrify. So typically, and these situations seem to have happened a few times. Product manager comes to a project engineer and says, "Hey, I want to build this fully electric machine for whatever trade show this fall. Let's do it." And so that kind of, the project engineer has to sit there and kind of, okay, get ready, let's go. And so these are kind of some of the steps if you're in that scenario. And obviously, hopefully it's not always that scenario. But these are some of the steps that we found you need to think about are pretty consistent between all methods and all processes, and then company-wise. So first thing, you have to determine how to push. How much does the actuator need to push? A lot of times with the hydraulic replacement, we just have one that just came up today. customer only has their cylinder and the pressure that it's running at. That's the way we like to start. We're going to talk a little bit more about the mean load. An actuator, because it has a ball screw in it, can do L10 life, so we can actually calculate an L10 life. So it helps to get the mean load to actually how we size the actuator. In an ideal world, we got some type of pressure curve where you've measured the pressures of the system as it's gone through its process or its cycle, and we can look at that and kind of pick a mean load. Ideally, we have force measurement on the rod itself, and you're actually measuring the forces, but that doesn't happen too often. But we can start wherever we need to start, we can do and kind of work through it. But typically it's, the more information you can have on the load, the better you're going to size the actuator. So typically we'll start, if you just give us piston force, the size of the cylinder and the pressure it runs at, we'll come out, we call that the max force typically. A lot of cases you may never get to that, but people size cylinders to very cost effective and have a lot of power density. So people put in what they need, sometimes bigger. But so the max force for us, we still want to get to the optimum. If you can get a measured force or a load profile, that's even better. Ultimately, like I said, we want to get to this application max force. And then ultimately, we really want to get to what we call the mean force. And then we can use that to calculate the life of the actuator. So with that, narrowed down, we'll click your actuator, and then we'll actually calculate the optimized actuator. Of course, I misspelled actuator. And then we will actually also give you the life calculation on that actuator. Once we get to that mean load, we can tell you what the cycles are. Unlike hydraulic cylinders, which I think are tough to really calculate life, with electric actuators using L10 calculation, which is proven in the bearing industry for a long time, we can actually give you a pretty good estimation on what the life cycle will be of that actuator. Just determining what that mean load would be in the duty cycle is a challenge. Move on here. Here's a little bit of a case study of a situation. Like I said, the customer, when they first came to us, they just had the max force of 50 kilonewtons. And as we worked through it and talked through it more, and they measured more and more stuff, we kind of got the load profile, the curved load profile here. And with that, we were able to kind of narrow down and get to the mean force. We did some analysis kind of on their duty cycles, and we were able to get to their mean force. Originally, we started out with a 50 millimeter screw to meet their life cycle that they wanted. Then we ended up going down. Once they got the mean force calculated, we were able to get to a 40 millimeter screw and really lower their cost by quite a bit. Also gets the size of the actuator smaller and everything else. So it's, the more we can get to that mean force, and like I said, this is a challenge sometimes. Some customers have the capability and some are just starting new. They just really know the pressures and the size of the cylinders. In general, I kind of use 30%, take the max force, maybe 30% below if we don't know where to start, kind of as a guideline just to get started, to get the right actuator. And then you can kind of look at it, get the models, and see how it fits as a starting point. But ultimately, that's something we have to get to, is what max force you're going to need. All right, next question is how fast. So obviously, speed defines the process. And the faster you go, obviously, is a big deal. But how fast do you really need to go? I guess for me, in the case of my loader, on my tractor, if it takes me 3 seconds versus 2 seconds, it's not a big deal to me. But maybe, we think about machine design and marketing people want to be able to advertise that. So that's just things to consider. It's a direct correlation. As we go further, typically on scissor lifts, maybe they're 25 millimeters a second. The forklift mass, maybe 300 millimeters a second. So quite a bit of variance there. The components that would be affected in determining that speed would basically be the gearbox, so the ratio, and then the screw in the lead, and then the motor and the size. So it's a direct correlation. Oops, sorry. It's a direct correlation between output power, your force times your speed gives you your kilowatt of your motor. And typically for electric actuator, we probably add another 30% to that to get the motor size. So obviously direct correlation. So sometimes you may have to compromise speed a little bit. Hydraulics, once again, are great power density. They can move fast. With electric actuators, your motor is at the source. So your motor is out there on the end of the mast. So you got to think about, do you really need that bigger motor? can you go a little bit smaller, or maybe go with 2 actuators instead of 1 to have 2 smaller motors? Just different ideas to kick around to get around the speed function. But that is something you have to determine and optimize what speed is best and what can you get away with. Duty cycle, kind of another big discussion. Does have a big impact on the cost. A lot of companies like ourselves that are getting into electric actuation for mobile machines started out in the automation business. Evolix was part of SKF, their linear motion group. So a lot of stuff we were doing are actuators designed for originally for in-plant automation. So it's 24 hours a day, 7 days a week. As we get into mobile and off-road, more and more duty cycles are smaller or lower. In the case of a scissor lift, obviously, somebody picks it up from a rental yard, they go and use it to paint their house or do work on a construction site, and then it goes and parks for a while, or they use it in a change a light bulb or something like that. So fairly intermittent. Excuse me, fighting the cold. Excavator may be a little heavier duty. They may use that 8 hours a day or 6 hours a day on site, and then it may sit for a while, but you just never know. Depends on the contractor or rental company. Those are just things we have to work through and think about your application and what fits optimally. It will impact all of these. So it will impact your motor type. I mentioned earlier, either a brush DC or a brushless or high performance motor. High duty cycle, we got to go with something high performance. Low duty cycle may get away with a brush DC motor, lower cost, that type thing. It also impacts your brake type. So I didn't talk too much about brakes, but on these smaller actuators in the marketplace that are under around 1 ton force, most of those have brush DC motors, and they have spring brakes, mechanical spring brakes in them, and they're designed for mostly 25% duty cycles. So if you're going to run that all day long in like a AGV application or automation application, it's not going to work. It'll wear out. So then you have to jump up to some other type of brake. On all of our high performance motors and other people's, they use, or high performance actuators, they use EM brakes. So it's a power off brake. It goes on the back of the motor typically. We can also put it between the brake and the motor, but typically goes on the back of the motor. And it's nice because when the power's off, it's engaged, so it's holding your load. As we talked about, a ball screw will back drive, so it will not hold your load. So you have to have some type of brake to hold your load while you're not working. But it's nice in the case of a loader application. You pick up the load, you raise the load, your brake engages, you move it across the working site. You're not using any power to hold that load in place. And then you dump the load and then the brake is disengaged. So it's just some neat features. Electromagnetic brakes, pretty common now. And typically we have to have those, and usually it's designed, for certain, in the application, we have to design it to holding loads. No brakes is an option. Some horizontal application, you may not need a brake, but so far we haven't done many of those. And then we've had a few applications where they want dynamic brakes. Typically the motor is going to stop your load, and then the EM brake just holds it. Some people wanted a dynamic brake to actually stop the load, so it stops more accurately, but we haven't had too many of those. And the last it'll impact is your screw size. Obviously, a 100% duty cycle, you're going to need a bigger screw to meet the same life versus intermittent duty cycle. You need a smaller screw. So anyway, higher duty cycle, it's going to impact your cost, but your machine is what it is, so you got to design for it. Just have to take it into account. Now, try to optimize that once again with the mean load. Those are important factors in trying to really optimize the actuator. So moving on kind of to the, how long does your actuator need to last? As I mentioned, we can calculate L10 life on all these once we get to that mean load. So, we can take your cycles and you can do all this and just double the stroke, and we come up with your cycles, and you tell us when you want it to last 10 years or 5 years. We can come up with that information. We can even, as things advance, telematics and then the actuators, we can measure the force that the actuator sees and the strokes that it's taken. And theoretically, when a rental company wants to go sell that machine, we could give you a life, what's left in that actuator theoretically. So that type stuff, that type telematics and data analysis is potential or possible with these actuators. But basically, just come down, like I said, the longer life you get, the lower that thing gets in the load capabilities. So it's just a calculation we can do. So typically in hydraulics, it's a little bit more of a challenge to come up with that type estimation, but actuators is pretty straightforward. All right, next one's more challenging. Kind of how do we want to mount the actuator? Just like hydraulic cylinders, we can put rod ends on each end. We can put clevises, pinholes on each end. Those are standard products for us, or standard mounting options for everybody. We found that this pivot type of attachment is best if you really want to look at pin-to-pin dimensions. If we go end to end like this and put a rear mount on here like this one, typically our pin-to-pin is going to be longer. It will be longer because of this gearbox and this motor that's in there. But with this pivot point, we found if you're trying to interchange a hydraulic cylinder, this gives you the closest pin-to-pin distance. But the downside, you still have to live with that motor and that gearbox. And then we live with what we call the tail swing. You have to take into account. Obviously, with that motor, it can be down there, so it has to fit into your frame. And in general, like I said, it's not a drop-in interchange. These things are typically you're going to have to redesign your frame to get these cylinders in there. It's just there's no getting around it typically. And this is, like I said, we found that the pivot point is your best way to go if you need pin to pin. But if you ultimately just can't do it that way, then like I said, these are open. On the pivots, we can do a male one like this. And you should drop it into some type of saddle. Or we can have a female hole there on each side, and you can pin it from the outside. So there's both ways out there in the marketplace. All right, voltage is a big discussion. A lot of places, what voltage do I use? My machine voltage may be 600 volts. But, what does my actuator voltage need to be? That's a big discussion. I guess ultimately it comes down, you have to decide. Some customers, I think, look, if it's a high work function, they want to use the higher voltage to get the most efficiency and get the less amps going out there and smaller wires. And maybe if it's a auxiliary function that's out there, only works once a day or something, they can get away with lower voltage. So the high power ones, they want to use higher voltage. And then on the less used applications, they may want to use the lower voltage, and higher voltage on the higher power density ones. Obviously, a case of safety, there's a lot more things you need to do for the higher voltage applications. There's some safety protocols. You can't leak voltage at all. So that's kind of some of the concerns you have to get into. As far as availability and what's in the marketplace, there's a lot more motors going into high voltage availability. There's not as many high voltage motors and controller people. In the 24 to 60 volt range, there's more people that do that. So it's more availability and more controllers that can do the parallel functions and things like that you'll need for as you move into more of these machines. So especially on like loaders and that type thing where you have to have 2 lift actuators or 2 tilt actuators in parallel, you've got to have that parallel function. But voltage wise, operator preference, like I said, some industries, they've got high voltage on the machine already, so they want to carry it over. Some places they're low voltage machines and they just want to keep that throughout their machine. So it just depends on the application. But in general, like I said, it's more and more, the higher voltages are getting more available. All right, so getting into controls, we kind of break it down to 3 complexity levels. Kind of low complexity, you really don't need positioning feedback here. You just have manual operation. Some operators pushing it down on a dump truck or a tail lift, and they're going to hold the button until it gets to where they need it. You don't have to program in a position or something like that. The operator determines it. So here I show a tail lift, low complexity system. You jump up into a little bit more where you need, say like on a street sweeper, and you want to dump the hopper in the back. And, the operator can't see that very well. So you want to be able to program in that position, when to get to stop and when to come down when it's back in its loaded position. So there you need a controller that has some position accuracy or controllability. You'll need some type of position feedback on the actuator. So it's a little more complexity, but it's still pretty simple. the guy holds the button until it stops and closes the button until it goes down. You're not putting in any type of force profile. You're not putting any type of soft start, soft stop, although you could. So that type thing is average. And then we get into more of the high complexity, where we've got some type of bus communication. Obviously, we got a controller. Typically, there's one controller for every actuator, and you're doing a lot of signals, and there's a lot of actuators on the machine. And so you just get more and more complexity. Here we show a combine. Obviously, there's lots of actuators on a combine, have been for years. Electric app part of it, and there's still hydraulic cylinders on there also. But there's just more and more complexity. You've got to talk to a lot of different devices. You need to know open those devices are open or closed, that type thing. So once again, you can get the external controller, or you can get, in some cases, the internal controller that's built into the actuator. Typically, the internal controllers are going to be limited to 48 volt operation. Maybe as the market expands, I think you'll see more and more people have higher voltage integrated controllers. But today, you need an external controller for the higher voltages and the larger actuators. Again, as you go forward, the expense goes up. I will say, I think as things go forward, it won't get as much. Just technology get better and availability gets better, and I think it'll come down. And you start integrating controllers in the actuators, it gets pretty cost competitive, cost effective. All right, a few special considerations. When you're looking at electric actuators versus hydraulic cylinders, just some things, different applications you got to take into account. I'm going to talk about a scissor lift again, but it applies to a lot of different industries. So if a scissor lift, you got somebody up in the platform, power goes off, you've got to get them down. With hydraulic machines, they pull a cable that releases a valve on the cylinder, and it's controlled valve, so it comes down a nice smooth motion, and it's not a joyride for the operator, and they get them down in an emergency situation. For electric actuation, you've got to do the same thing, but the way we do it, and this will be applicable for other places where you've got to get a load down if it's in a raised position, for loaders or tailgates on garbage trucks or cranes or something like that. So in the case, what we can do, or actuators you can do, as you talked about, we had an electromagnetic brake that goes here, and that's what holds the force. That's what holds the scissor up. And there's a lever, mechanical release here, and you attach your cable to that, and then you open the brake, and then the actuator will fall. But because of the efficiency of the ball screw in the system, it'll fall too fast, so it doesn't meet regulations. So we had to add a centrifugal brake into the system, which basically adds friction to the system, so it controls the descent. So that's just another feature that can go, in our case, it can go on the back of the gearbox, or it can go between the motor and the gearbox. But that's just kind of another feature. As we show here, we can do different attachments on the rear, the pivot attachments. The other thing a lot of actuators have is a mechanical operation or a manual operation. So you can put a power screwdriver on here and drive the actuator in case you need to retract it or extend it. Some people use that in manufacturing because they want to get your actuator set to a certain position to assemble in the machine. So that feature is available on a lot of actuators. And like I said, the manual holding brake we talked about earlier with the mechanical release. The other safety feature that's available on some actuators is a backup nut. Once again, if you've got a person involved, they've got to be able to get that machine down. If the ball screw fails, then they'll ride on this backup nut, and then they can still move the actuator down, albeit very slowly. They can move it down and get the operator off, and then fix the actuator. But that's just a safety feature that's available. But a lot of these things I think can be used on different applications wherever you're lifting a load. You don't want, if it's gets some odd reason the power goes off when you're in up position, you can kind of get it down and move on to the next step. One of the big considerations that come up a lot is mechanical shock. So here you've got, obviously, electric actuators or hydraulic cylinders have built-in absorption, right? They can take impact. They've got give in them. Electric actuators are pretty rigid. There's not a lot of give in them. We personally have done a lot of testing. Ours are a lot tougher than we thought they were. But there's still a point where, you have to do something to the actuator to help it survive some of those severe impacts that you see in certain applications. The other situation you have is, it's not going to absorb that shock and it's not going to dampen that shock. So we're working on ways where we can actually use the actuator to help dampen the shock so that it doesn't go to the machine. So those are some situations where hydraulics, there's solutions. With electromechanical, those are still solutions that are being developed. There's some people that do have some ideas out in the marketplace. For us, we're still developing some ideas in that arena, but those are just some things you have to think about and address. And it's kind of to me, it's still a learning curve, what they can take and where they're going to go and end up. So those just kind of come as special considerations to take into account outside of just the regular day-to-day stuff. And then moving on, just kind of a quick summary. And then we'll open up to a few questions if you have any. Number one, determine the force. Ideally, once again, if we can really get into some mean loads, the better information we have, the better we can optimize it for you. Settle on an optimal speed for your application that you can live with. Once again, higher the speed, the larger the motor. Duty cycle, life cycle target, that really is what it is. So you just have to figure out if we can define it. There's always a little bit of a challenge. Actuator configuration, once again, there's not a lot of options. We know what we like or what works best, but may not fit in your application. So we have to go with the rear mount, that type thing. What actuator motor voltage do you want, for your application? So you kind of have to settle on that. And then last, the control package. Do you need just simple relay start and stop, that type thing, or could you need a controller that gives you position feedback, that type thing, or do you need a full CAN bus type system? And then, like I said, a few special considerations, safety, emergency situations, and then last, impact and the space claim are the biggest challenges, I think, to electric actuation, and cost, I think, will have an impact. Typically our actuators, depending on the complexity of your system, are going to be a higher entry-level price than your hydraulics systems. And with that was the end of my presentation. I'll turn it back to Zach.
All right. Thank you very much, Kirk. A very good presentation, and apparently so good that you have not received any Q&A from the chat.
Okay.
I guess I'll enter a few of my own questions here.
Okay.
So one thing that I've thought about before is package size. So when you look at the system and the package included for hydraulics versus electric, are there drop-in replacements available, or are there some special design considerations that need to be made?
No, as I kind of mentioned, it's rarely going to be a drop-in. It might be able to be pretty close on a smaller system, but typically that motor and gearbox is always going to cause some redesign to the frame, probably 10, 20, 30% type of sizing. So you're going to have to redesign the frame, and it'll impact your stroke length and everything else. But if you do the pivot points, that'll give you the best pin-to-pin fit in, but you still have to accommodate for the motor and the gearbox on the backside.
Okay, and then just one more. I know you talked about voltage a little bit there during the presentation, and talked about the pros and cons of lower voltage versus higher voltage. Is there a general rule of thumb on that when someone's considering moving away from hydraulics, or is it very specific to the application?
To me, it's kind of the size of the machine. I think some of your smaller machines, lower duty cycles, maybe like service cranes or work truck space, or maybe small walk behind construction equipment, that type thing, where they can get away with smaller voltages on the machine itself. Then they can use smaller voltages on the actuators. When you get into bigger machines, you got to have more high performance, and they've got higher voltages on the battery package. There's where they have to look, and we have to consider, do you want full voltage at the motor, or do you want to use lower voltage at certain positions on the machine? So it's kind of a balancing act, and it depends on the platform voltage.
Okay. Thank you very much. I guess in lieu of, I guess there is one question that came in. So somebody had come in late and asked about what the benefits, if you showed them what the benefits are of the electric actuators over hydraulics. Maybe if you want to just talk very briefly about that.
So the benefits, there's 5 main ones, I guess. So the two that are most common or most people look at is no oil. So in oil, you can get an oil-free machine for certain environments that's desired. The efficiency, as we get into battery-powered machines, the more efficient you can make the machine, the better. So typically your electric actuator can be more efficient than hydraulics. So those are the two main ones. Some of the other areas, controllability, like if you're doing grading machine work or stuff like that, the controllability on the actuator is a lot more precise typically than hydraulics. There's no play. And then the few other key items, there's no maintenance required. So that helps your TCO, if you will. And then also there's a smaller BOM. There's just less parts on the machine. So it's more simplified as you go into manufacturing and obviously maintenance and aftermarket, that type thing. There's just fewer parts. And those are kind of the 5 key whys. Each customer kind of has their own reason why they do it, but those are some of the 5 main reasons.
Okay, looks like my questions may have sparked a few more coming in. So there's one here. What applications work well with direct drive to eliminate the gear ratio and for density and efficiency?
We haven't done many of those, to be honest, in the mobile world, because usually we're going lower speeds. So typically, where you're not going to have a gearbox, it's going to be high speed, low loads. I haven't seen that in any off-road applications. Almost all the off-road applications, there's been a gearbox involved because we need the torque to downside to go through to get the torque to the drive shaft that we need. So typically, it's going to be more in high-speed, low-load applications. You may find in more automation type applications.
Okay, and one more that came in here. Can you touch on durability and reliability in, say, rugged, dirty environments, maybe mobile excavators, and looking at the hydraulics versus electronics?
As far as hydraulic replacement in mobile environments, so it's pretty new world. But all the actuators are designed for IP ratings for mobile. There's testing for the vibrations and the wash down situation. So reliability and durability, they hold up well. Like I said, there's not a lot of machines out there that are in production to kind of prove that point. But on the smaller actuators, they've been in production for a long time by a lot of people on ag machines, and smaller machines that lived in that environment have survived well. So there is, I think, some perception. You've got to size it right. You got to get the right actuator in the right application. So I think there is some situations where electric actuators haven't survived well. It's just a matter of how you design and get the right actuator. For us, we put like a venting systems in ours because a hydraulic or electric cylinder is like a big pump. So it's going to suck moisture in. So we kind of have a venting system in ours so it won't gather moisture and suck moisture inside. Just things like that you have to take into account. But in general, they should last. They can survive the environment. Like I said, the big unknown is still kind of impacts and vibration especially on construction machines.
Okay, and then one more question about lubrication. So are there any lubricants used in the actuators? And if so, what are they?
So typically the gearbox is filled with grease, so it really doesn't need to be serviced. And then the ball screw nut is greased. It has a relube port typically from different manufacturers. So you can re-grease the ball screw, but a lot of cases you really don't need to. And then some people on the pivot points, they like to re-grease on the pivot points. So those would kind of be the maintenance areas. But in general, they're pretty much maintenance free if you get the right setup.
Okay, one more came in. So I know that you mentioned that there's some ongoing research and development to compensate for shock. For existing applications, is there any risk to using electric actuators with hydraulic designed brackets?
No, I mean, like I said, we just got to size the actuator. Some people, what they've done is they've oversized the actuator to be conservative. So they put in a bigger ball screw than maybe the loads determine it needs. So to go in, like I said, it's kind of a new area there's not a lot of data. Like I said, we've done some testing on our actuator where we've brought impact to it and it survived pretty well, better than we thought, to be honest. But it's kind of a growing area and unknown. We've got a few solutions we're working on to help minimize that impact to the actuator. But in general, I think you just got to look at the loads and kind of size the ball screw and be maybe a little conservative on getting the right ball screw in there.
Okay. That seems to be the last question, Kirk.
Okay.
So with that, thank you very much for presenting and sharing your expertise here. And
Okay.
thank you all for attending.
All right. Thanks, Zach. Have a good day.